Hi, welcome back. I'm Mr. Peck here. Now we are going to learn about simple harmonic motion. What is actually simple harmonic motion? Simple harmonic motion is actually a motion that repeats itself over and over again after a certain period. Okay, let me show you an example. Uh, Here we have a spring mass system. It exhibits the simple harmonic motion. Okay, we always call it an oscillation. Let me show you. Okay, let's play. See that? The spring mass system, it oscillates up and down, up and down, up and down. Repeat itself over and over again with a certain period. So as it oscillates up and down, it forms a sinusoidal graph. Okay, actually this is a cos graph. Form a cos graph. Okay, now another system is called the circular motion. Circular motion is also a simple harmonic motion. Let me show you. Okay, see that? Oscillate up, down, up again. What you see here is actually the y component of this circular motion. As this point going up, this point also going up, and then goes here, back to the equilibrium, go back downward, go back to the equilibrium point. See that? So a circular motion is also a simple harmonic motion. Okay, now I just want to do a summary on this chapter, okay, and also some derivation of the very important formulas inside the simple harmonic motion. Okay, let us start with displacement. Okay, before I continue further, in the past you have learned about linear motion. Linear motion is actually motion that going to the left, right, up and down. Okay, and after that we learn about circular motion. Circular motion is something turn around. Okay, make a circle. That's called circular motion. Now we have learned about simple harmonic motion. It's about oscillation of objects. Whether it is a simple pendulum or maybe it's a spring mass system, oscillate up and down. Okay, this one oscillate left and right. Okay, so all this while in linear motion, we learn about displacement, velocity, acceleration. Okay, we learn about displacement, velocity, acceleration. In circular motion also we learn about angular displacement, angular velocity, angular acceleration. So now in simple harmonic motion, we will also learn how to find the displacement, velocity, and acceleration. Okay, they have their own formulas. Like you see, this is the displacement formula, this is the velocity formula, and this is also the acceleration formula. Okay. Also, you learn about potential energy and the kinetic energy. Yeah. Before this, linear motion, circular motion have their own provisional potential energy and also kinetic energy. So in simple harmonic motion, we also have potential energy and kinetic energy, because you see this thing is oscillating, it is moving, of course it has kinetic energy. Okay, so this is just you just treat this simple harmonic motion as another kind of motion aside the linear motion and circular motion. Now it is the third kind of motion called simple harmonic motion, yeah, or oscillation. Okay, just now we have seen this diagram, a circular motion, and we are actually relating the circular motion to the simple harmonic motion, oscillate up and down. Okay, actually we just consider the y component of this motion. Okay, you see this thing oscillate up and down? It's actually the same thing as the spring mass system oscillate Okay, let me show you. You see, it's the same as the spring mass system oscillate up and down. It form a sine cosine graph. Same thing with this one. This one also form the sine graph or cosine graph. Okay, and how actually do we get the sine graph or cosine graph? Look carefully. Okay, now I want to start with displacement. You see this? This is a circular motion. Okay, this circle has radius a. Actually, the radius is the amplitude. Is the amplitude, because when this object goes up, this radius become the amplitude, isn't it? Okay, so as this object going round and round, okay, we can also say the y component is oscillating up and down, up and down. This A, it has two components. Okay, it has two components. It has AX and also AY. So what we consider is actually only the AY. We don't consider the AX. Okay, and the AY. So this is also the AY. Okay, and the AY. This is actually the AY. Okay, the component that form the sine graph is actually the AY. How to get AY? AY is actually we have theta here. If we look carefully, okay, we only consider the y component of the radius. Y component of the radius. So the radius has angle theta. So AY is actually A sine theta, isn't it? Because it is AY is opposite the angle. Opposite the angle is using sine theta. So AY is actually A sine theta. Or we can say no angle, we use sine theta. So AY is A sine theta. So that's why. So actually this X, we use X. Actually this X is AY. Okay? AY. But we just use X because we want to treat this AY as the displacement. So we just use X. Okay? So AY is actually A sine theta. Like this one. See? X. This X is actually the AY. So AY or X is equal to A sine theta. Yeah? Sine theta because it's opposite the angle. And we have learned that if we look at the linear motion, we know that S equal to ut. Displacement equal to velocity times time. So that's why theta equal to omega t, because S is like theta, U is like omega. So S equal to ut is like theta equal to omega t. This is in terms of rotational motion. Okay, we are talking about rotational motion. So theta is the angular displacement and omega is the angular velocity. S equal to ut is like theta equal to omega t. So we substitute the theta with omega t. Substitute inside. And that's why we get this, the first and the most important formula in simple harmonic motion, which is called x equal to A sine omega t. Okay, why omega t? Because theta changed to omega t. Okay, so this graph is actually based on x equal to A sine omega t. Why is this a sine graph? Because sine omega t. And the amplitude is A. So the A actually is the radius. You see that? The A actually is the radius. So A is the amplitude. Okay, this omega t initially is theta. Okay, so this is how we get the first formula, displacement versus time formula. Displacement versus time formula. X equal to A sine omega t. Okay, so we already have the first formula, the displacement formula. Now we want to get the velocity formula. How? How do we get the velocity formula? Velocity versus time. So same like before, v equal to ds dt, isn't it? V equal to ds dt. The gradient of displacement time graph. So, all right. So now, v equal to dx dt. So we differentiate. That means we differentiate the displacement versus time equation. We differentiate it. So a sine omega t, we want to differentiate. How we differentiate? So we differentiate outside, then we differentiate inside. So we differentiate outside. We differentiate A is still A. If we differentiate sine, we get cos. We differentiate sine, get cos. And then we differentiate, we differentiate sine, we get cos. After that, omega t, we just copy back. And then we differentiate inside, we get omega, isn't it? We differentiate inside, we get omega. So times omega. After that, this omega just multiply to the front, okay? And that's why we get v equal to a omega cos omega t. So we got the second formula, velocity versus time formula. V equal to a omega cos omega t. Now, we want to get the acceleration formula. Acceleration formula. Okay? So the next formula is acceleration versus time formula. So we use a equal to dv dt. This time we differentiate the velocity time graph. We differentiate the velocity time equation to get acceleration. So we differentiate it. Okay, just copy back a omega cos omega t. We differentiate with time. Now we differentiate outside, then we differentiate inside. Differentiate outside, we differentiate the a omega is still a omega. Then we differentiate cos, we get negative sine. Remember, when we differentiate sine, we get cos. We differentiate cos, you get negative sine. Don't forget the negative sign. Very important. Differentiate cos, you get negative sine. Okay, then omega t just copy. And then we differentiate inside, we get omega. We get omega. So this omega multiply to the front, and that's why we get here omega multiply to the front, here become omega square. So a equal to this negative drag to the front, a equal to negative a omega square sine omega t. I hope you know how to differentiate this trigonometry formula. You already learned this in your mathematics. Okay, so just apply your mathematical knowledge of differentiation into physics. Okay, all right. So now we already got the three formula: displacement, velocity, acceleration for simple harmonic motion. Okay, but these three is versus time: displacement time, velocity time, acceleration time. As you can see this formula, we have displacement and time, velocity and time, acceleration and time. Okay, now sometimes the question will give you, will ask for, let's say, it give you displacement, and he asks the value of acceleration. The question gives you displacement, and then you need to find the acceleration. Now you have to use the acceleration versus displacement equation. You already have acceleration versus time equation. but you don't have acceleration versus displacement equation yet. AX. We have AT, but we don't have AX. So now let's find the AX formula. We also use the formula of AT, AT formula. Okay, as you can see, I rearrange. I saw here we have A here and sine omega t here. A and sine omega t. So I combine them, A sine omega t, and then omega square and negative in front. Okay, so this one I put in bracket. This is A sine omega t. Just the same as x equal to A sine omega t. Okay, so A sine omega t, we can substitute A sine omega t with x. Use the xt formula. A sine omega t we substitute with x. And this one we substitute with x. And that's why we get what? We get A equal to negative omega square x. So this is the AX formula. Last time we have AT formula, A versus T formula. Now we have A versus X formula. A equal to negative omega square x. And this formula is the symbolic equation for simple harmonic motion. It's the most important equation in simple harmonic motion. Why is it important? Because it describes the meaning of simple harmonic motion. Okay, what are the two most important meanings carried by this equation? First, as you can see, this acceleration is proportional to x. So the higher the x, the higher the acceleration. First point. Second point is the negative sign. This means that the acceleration is opposite direction with x. That means if x is positive, A will be negative. If x is negative, A will be positive. And because negative, positive. So the negative signs means acceleration is opposite direction with x. Okay? So these two keys, acceleration proportional to x and acceleration opposite direction with x, these two becomes the foundation behind simple harmonic motion. So if people ask you what is simple harmonic motion, you just say, first thing, the acceleration is proportional to x. Second is acceleration is opposite direction with x, which is described by this formula, A equal to negative omega square x. It is the motion, simple harmonic motion is a motion where the acceleration of the object is proportional to the displacement of the object. Secondly, the acceleration of the object is always opposite direction with the displacement of the object. So these two means it is a simple harmonic motion. Good. Now you already have the AX formula. We want to find the velocity x formula. We already have velocity time formula. Velocity time. If the question gives you time, you can find velocity. But if the question gives you displacement and asks you to find velocity, you need the velocity displacement equation. Okay? Let us derive. First of all, to get the velocity displacement equation, we will use both of xt and vt formula. We will use. So xt formula is x equal to a sine omega t. This omega t I just changed to theta. Okay, theta. So I rearrange this formula. X equal to a sine omega t become sine omega t equal to x over a. That means this a just go below x over a. Also, we use the velocity time formula. V equal to a omega cos omega t. This a omega go below. Okay, V over a omega cos omega t v equal to v over a omega. Okay, theta is omega t, s equal to ut, same thing. So now we start with the trigonometry identity called sine square theta plus cos square theta equal to 1. Everybody knows this equation, right? Okay. So for the displacement time equation, I have sine theta. For the velocity time equation, I have the cos theta. Okay? So we use both of this formula, substitute into, okay, like the sine theta is x over a. This is omega t is theta. You know, sine theta equal to x over a. I substitute into here. So here become x over a square. And then the cos theta, I substitute with v over a omega. I substitute here. So here become cos square theta become v over a omega square. Okay? So now you see, we already have the formula for v versus x. We already have the formula v versus x. Now you just make it simpler. Square both, expand this, and then multiply a square omega square. Okay, so we get this. After that, this one go to the other side, and then we factor out the omega square, and then we square root both sides. We square root both sides. The square gone. Here becomes square root. And then when you square root both sides, remember to add the positive negative sign. This positive negative sign very important. Okay, this positive negative sign just means the direction. The direction, yeah, can be direction. Positive negative means can be upward or downward. Okay, so this is the equation for velocity versus displacement. Velocity versus displacement, Vx equation. Last time is velocity versus time equation. Now this is v versus x equation. Very simple, isn't it? Yeah. So we already have 5 formula. We have xt formula, we have vt formula, we have at formula, we have ax formula, we have vx formula. Okay. Now, what formula we want to find further? It is the potential energy and the kinetic energy formula. Okay. Now, last time you see about this thing. Okay, the spring mass system oscillate up and down. Okay. Wonder why this is not moving. Okay. For the spring mass system. See, spring mass system. The spring, inside the spring is stored elastic potential energy. Elastic potential energy. And then the mass, the object, it is moving with velocity. So it also shows kinetic energy, half mv square. Okay, elastic potential energy is half kx square. Okay, it depends on expansion and compression. The spring has elastic potential energy, and for the mass, the object, the block, it has kinetic energy, because it has velocity, half mv square. Okay, half mv square. So we have elastic potential energy and kinetic energy. Now, let's look. So for elastic potential energy in the spring is half kx square. Half kx square. Okay? So yeah, here one thing. The k is the spring constant. It is the spring constant. This spring constant is equal to m omega square. M omega square. This one actually derived from another formula. Okay? You just remember k equal to m omega square. Mass times angular velocity square. Okay? Now, So you just substitute k equal to m omega square, then you get u equal to half m omega square x square. So this is the formula between u and x. Okay. Now, how about kinetic energy? Kinetic energy is the kinetic energy of the block just now. The block just now going up and down. It has a velocity, so half mv square. So now v, you substitute with this formula, Vx formula, this one, okay? Now we substitute the v with this formula, and that's why we get k equal to half m omega square. The square root just gone. A square minus x square. Positive, negative, after you square, the negative also become positive. So no more positive, negative. All positive. Okay? So here, you get the formula between kinetic energy with displacement. Kinetic energy with displacement. So you have potential energy versus displacement equation. Now you have kinetic energy versus displacement equation. After that, because we see, if we look carefully for this spring mass system, the energy is always interchange between elastic potential energy and kinetic energy. Sometimes the energy stored in the spring, sometimes the energy stored in the object, in the mass. Okay. Sometimes the energy stored in the spring as elastic potential energy. Sometimes the elastic potential energy convert to the kinetic energy of the mass. So they are interchangeable. So that's why the total energy of this system is always constant, because the energy just changed from elastic energy in the spring and then change back to the kinetic energy in the mass, changing just convert to each other. And you see, there's no damping happen. No damping happen, so no loss of energy. So the total energy is always constant. The energy just changed from elastic energy to elastic potential energy to kinetic energy. So the total energy is always constant. It's between potential energy and kinetic energy. So the total energy is always between these two, potential energy plus kinetic energy. So U plus K. Okay. So now the elastic potential energy formula substitute inside. The kinetic energy formula also substitute inside. We substitute both formula inside here. So total energy is U plus K. So we get this. You see? This one and this one, you see here got x square and here got negative x square. That means these two can be cancelled out after this one expand. After this one expand, they can cancel out because one is positive, one is negative. So at last, we get the total energy formula, which is equal to half m omega square a square. Half m omega square a square. And this is a constant value. Because, why constant? Because the spring mass system, no damping happen. No loss of energy. The total energy, we can say this oscillation will no loss of energy, this oscillation will continue indefinitely, will continue forever, because the total energy is always constant. Just convert between two forms of energy. So the total energy is always constant, which is half m omega square a square. Okay, and so so the formula of this is the formula for between total energy with the displacement. For total energy, the displacement is the amplitude. Okay, is the amplitude. So the total energy is half m omega square amplitude square. Yeah, and this is a constant value. And this value is also the value for maximum potential energy or kinetic energy. maximum kinetic energy. Okay, the maximum potential energy is also equal to this value, this formula. The maximum kinetic energy is also equal to this formula. Okay, because there's one point, all the energy stored in the spring. So the total energy all totally stored in the spring. Okay, and sometimes the total energy all become the kinetic energy of the mass. Okay, so so this is the first part of a summary. So see you again in the next part of the summary. Bye.